Hello everyone, welcome to Stochastic Calculus for Finance 1. We are now tackling the sixth chapter, which is on interest rates dependent assets. So first we're going to start by section 6.2, the binomial model for interest rates. And this is part 1. So here's the first goal in this section. The goal that we have here is just to define the main element that we'll be using throughout this chapter. So first we'll just give a very basic definition of fixed income assets. Then we're going to talk about the interest rate process. So now we're allowing interest rate to be stochastic. So we need to define exactly which stochastic process interest rate will follow. Then we talk about the discount factor process, because when you have stochastic interest rate, naturally you have a stochastic discount factor process. Then once you know how to discount cash flow, we talk about zero coupon bonds. Then we can talk about the concept of a yield on a zero coupon bond. Then we can talk about the yield curve from here. And we'll have a quick discussion on yield curve models. So I think this section on interest rate modeling is very, very, very important. When I first joined the market, just the job market, working in a for-quant bank, I was very surprised to see how much focus and how people are interested into interest rates modeling. And that is because the fixed income market is way larger than the, let's say, the equity market. And so there's a lot of interesting work done here. So I think the time that you will be spending investing on listening to this section, have very good, I think it's going to be paying off for you and for your career. So let's go. So if you're following this course up to here, I'm pretty certain that you know what a fixed income asset is. But this has been covered in the book, so just to make sure we're on the same page, I'm just going to give some very dumbed down definition. So fixed income assets is an investment that's providing, in the key here, periodic returns. So we know when the cash flows are going to be received. And typically the principal will be returned at maturity. So if you invest, let's say, $100, so typically at maturity, you'll get back your $100. So that is what all this, very simply what this means. Then since naturally we're talking about fixed income assets, so we can think that interest rates are going to play a very important role. So these are assets that are very sensitive, or at least interest rate is very important when we're talking about these assets. And typically, like, people like to invest in this because they are typically less volatile than equity. They have maybe lower correlation with equity, so there might be some benefits from diversification when you create a portfolio of both equity and fixed income. And this is just a quick example. So this is called, like, this is just a 5-year semi-annual bond, and we can see the cash flow. At the beginning, you have an outlay of $1,000, and every 6 months, at regular periodic return, you're getting some return, and at the end you get back your principal and also the coupons. So first, let's talk about this thing that we're calling the interest rate process. What is this interest rate process? Here we're allowing interest rate to be stochastic, so we need to define a stochastic process on this. And the definition, as you would see, is very simple. So let omega be a set of 2 to the power n possible outcome from n coin tosses. What does this mean? That means basically you simply take a coin, right, and you toss it n number of times. And that is just like basically, if you toss a coin n number of times, then you can have to the power n possible income, because you either get a head or tail, and you do that n time. And we can give a general notation as this, just omega 1, omega 2, omega 3. And for example, maybe omega 1 is just a head, and then the second coin toss was a tail, and the last coin toss potentially was a head. And so one particular outcome could be noted by, for example, H, T, and maybe the last coin toss was a H as well. Very simple stuff. So we can define then a probability measure on this universal omega. And the interest rate process is simply a sequence of random variable. And I have here the timeline. to help us maybe visualize a little bit while we're going through this definition. So it's a sequence of random variable R0, R1 up to Rn minus 1. And as you can note here, then we have n number of R's here, where R0 is not random. And R0 is not random because if you stand here today and you go to the bank can tell you how much your money will grow if you want to invest it for one period, right? But in the future, once you get your money back and you want to invest it again for another period, you don't know exactly what that is. So that is a stochastic variable, a random variable. But at least the first point of time, if you go to the bank today the bank can tell you what the interest rates levels are. So that's why basically R0, which is the first one, is not random, but R1 is potentially random. And R1 is going to be the interest rates from period 1 to period 2. And Rn is, let's say, the interest rate from period n to n minus 1. And if your n horizon is this n here, then that is going to be basically the interest rates. N minus 1 is going to be the interest rate at time n minus 1 for an investment that will go from n minus 1 to n. Very simple stuff here. And for any n between 1 and n minus 1, we have Rn depends only on the first n quantus. And that makes sense. So R0 depends on no quantus because it's not variable. But then R1 will depend on the first quantus. So maybe once you get that money back after the first period, if it's a head, maybe interest rate goes up by 1%. If you get a tail, interest rate goes down by 1%. So the interest rates at period 1 will depend only on the first quantus, and the interest rates R2 will depend on the first two quantus, right? Because we get the quantus from time to find the interest rates that are going to be for an investment from period 1 to period 2, and R2 is the investment from period 2 to period 3. So you're going to toss the second time. That's going to impact that. And so that's what we have basically just for the definition of the interest rate process. Okay, now that we understand the interest rate process, now we can start talking about what we call the discount process. And very simply, the discount process is defined by simply this expression here, this thing here. And to be able to give more background on this, so try to understand it, let's pull a timeline here. So let's say we have a zero coupon bond or a cash flow something that pays $1 at time 1. If you find the present value today, all right, so we just take the interest rates and then we take this $1 and we discount that to the present. And then we know the interest rates at time R0. At times, the interest rate that we use for this is just this R0, right? And let's say now, instead of that, we had a cash flow that of $1 at time 2. So then what we need to do is take this cash flow, bring it back to 1 year, and then we bring it back from 1 year to today. And that is just essentially going to be this element, this part here, and so on and so on. So dn, the discount factor for cash flow occurring at time n, is just going to be essentially defined by this. So d2 would be the amount of the discount factor we need to apply to discount the cash flow that occurs at time 2. It's just going to be R0. We need to take into account the first interest rate R0 and the second interest rate, which is R1. Very simply. So that is simply, and of course, because R1, for example, and others are stochastic, they depend on the quantus. So naturally, dn also will be stochastic. It depends on the quantuses as well. Fairly simple. And something to note also is that actually this dn, it depends only on the first n minus 1 quantuses. And we show that, right? For example, d2 will depend only on the first quantus because R0 is not random, but the interest rates from time 1 or period 1 to period 2, we need to toss the coin, and if it's a head, maybe we go up, if it's a tail, we go down. So that will depend only on the first coin toss, and so on. If we look at the generic time period here, right? So to be able to discount from time n plus 1 to today, that will depend only on the first n coin tosses as well. And this is what all we mean when we say discount process. Again, very simple stuff up to now. Okay, let's now talk about this thing whether we call the zero coupon bond. And this is really the simplest form of fixed income assets. It is simply a bond that pays a specific amount at a given time M. And again, to help visualize that, we have a timeline here. And let's say at time M, we're getting a certain cash flow. Let's call this, for example, X. Then to find the present value of this cash flow, then naturally we just need to discount this cash flow to the present. And in our setup, that would be just basically we're taking this cash flow, discount it from time M to M minus 1, then discount it back, keep discounting back because these are the interest rates, this R0 that we know. And we know what this is. This is just what we're calling basically the discounting process, DM. All right. And so let's keep that in mind. So so naturally, what we said, to find the price of this cash flows that at time M is just given by this expression due to risk neutral pricing, right? It's just the expected value discounted to the present. But then the discounted factor is actually inside this expectation. And the reason why we have this expectation is because this DM, this guy here, is not known because it is stochastic here, right? It depends on the coin tosses that we have. And just as a reminder, we can see above here that essentially it is dependent on the first, DM will be dependent on the first M minus 1 coin tosses. So we need to take the expectation here. So naturally then, very simply, if this is just was like $1, right? If this was 1, then to find the price of the zero coupon bond that pays $1 at time M is just denoted by this expression here. So very simple on zero coupon bond. It's just basically you just take a down cash flow at a given time M in the future, and then you discount it to the present. And naturally, because now we're allowing stochastic discounting, stochastic interest rates, we need to be able to take the expectation. And this is just under the risk neutral world. This is just the risk neutral pricing that we have seen before. Nothing new, nothing too mysterious so far. Next, let's now talk about the zero coupon bond yield. So the zero coupon bond yield is just a single number that we're calling YM, such that satisfies essentially this relation. So the value of the zero coupon bond, right, is just given by this expression here. You stack the YM such that this expression is true. So that means essentially by investing B0M in the M maturity bond yields $1 at that time N. So essentially, when we're looking at our timeline again, right, we can see, for example, if you have a cash flow that occurs at a given time, we have to discount it first by this M minus 1 interest rates, and we keep discounting at some interest rates. But these are essentially stochastic, right? So they keep changing. So we want to find basically, if we look at the market, we know the value of a certain zero coupon bond. We want to know what is basically the single YM, the single number, right? Such that when I plug it inside, when I discount it with that cash flow, I can get the current price of the bond. So that's all there is to it, really. So then naturally, by just some minor algebra, we can actually extract the value of this ym given by this equation right here. So now that we know what the yield of a zero coupon bond at time M is, then we can start talking about yield curve. And to essentially to illustrate what the yield curve is like, we have our timeline just like before. And now we can think about it that we're adding now y-axis, right? And on this axis would be, it will help us basically to plot the yield that we have seen. And we have seen, I'm just noting here basically the formula that we found for yield of a zero coupon bond. So let's say, for example, we want to find y when m is equal to 1. So let's say we have a zero coupon bond that we are seeing, and we know what the price of the zero coupon bond is, $1. And we know the value, the price today. We know the value of what we're calling B01. Then naturally we can use this this formula that we have here to find y1, right? So let's say we do that, right? And we find essentially y1, right? And we plot it. We plot it. So you plot it at time 1, then we can find y2. And essentially we can keep doing this for all these time frame that we want. And we can plot essentially what the yield is, right? So this number here represent the yield for zero coupon bond that is maturing at time n. Very simple. So now we have all these data points. We can think about it as a curve. We can think that there is a curve that's going through this, so that if you want to discount basically tomorrow, naturally some interpolation is done. But let's say tomorrow we have a cash flow that is occurring strangely at a given time here in between. We can find that we can have a pretty good guess that maybe the yield on this the yield for zero coupon bond that maturing at this time here would be essentially around this place, right? So this is essentially what a simple yield, what a yield curve is. So when we say talk about now yield curve models, so what we mean by that, so we need to now find a way, because maybe today the yield curve looks like this, but maybe tomorrow the yield curve will look something like this. So over time, the yield curve can change shape and format. So we need to find a way of really being able to model all these different movements of this yield curve. And we need to be able to do it in such a way that does not allow arbitrage. And typically, that's what yield curve models do. So, and another way to visualize this is by looking at it this way. We can essentially have a 3D plots, right? So maybe in 2014, the yield curve was looking something like this, right? And then, but maybe back in 2006, the yield curve looked like something completely different. So essentially, you can think about as type of 3D plot where this is the time, and at each time or each date, we have a given yield curve. And we want to be able to model this in a way. We need to have a mathematical model to basically, let's say, generate this, how this yield curve could change over time, without really allowing arbitrage. And that's what these yield curve models are really doing. And there are many different types of yield curve models. You will hear things like whole Y2 factor, etc. But I think I will have later on a more another training course. And really in this field, what I can find is that this book by Damiago Brigo Fabio Mercure is really the book, at least the most basic book, and a little bit like the Bible for these interest rate models. And they go really in good details in it. But I just want to talk about them really quickly, just to give you a flavor, an idea of what it is. And maybe later on, I will go through these books and make videos on this. All right, so we can have a quick recap. So really what we did, we talked about fixed income assets, give a very brief, dumb definition. Then we talk about interest rates process, right? It's just basically you flip the coin, and basically R0, the interest rate today is known, but then when you at time 1 you flip the coin, and then the value of interest rate will depend on that coin, for example. So this is the binomial model of interest rates. And then we know what interest rate is stochastic. So naturally, discounting based on those interest rate will be stochastic. We introduced that. We talked about the zero coupon bond, the yield of a zero coupon bond, and just talk about a little bit about yield curves and yield curve models. So thank you for watching this video. I hope that this is going to be helpful to you. Thank you. Bye-bye.